This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to this discussion. Today, we'll be delving into a research paper titled One to Rule Them All: Natural Language to Bind Communication, Perception, and Action. This paper proposes an advanced architecture for robotic action planning that integrates communication, perception, and planning using large language models, LLMs. What are the key challenges this architecture addresses in the field of human-robot interaction?
The core challenge lies in enabling robots to understand and respond to complex natural language instructions in dynamic, unpredictable environments. Traditional robotic systems often rely on pre-programmed instructions or limited predefined knowledge, hindering their adaptability. This architecture aims to overcome this limitation by leveraging the power of LLMs for natural language understanding and reasoning, combined with robust real-time perception and adaptive planning.
The paper mentions the integration of LLMs within a modified React framework. Can you elaborate on how this framework enhances the robot's ability to translate natural language commands into executable actions?
The React framework allows the LLM to alternate between reasoning and action phases. Our modification extends this by incorporating real-time environmental perception and feedback from physical actions. The LLM receives the user's command, accesses environmental information through perception actions, plans a sequence of high-level skills, and then executes these skills through skill actions. The feedback from each action updates the LLM's context, allowing for dynamic adaptation to unexpected events.
The paper highlights the use of scene graphs as a semantic mapping tool. How does this structured representation of environmental information contribute to the system's robustness and adaptability?
Scene graphs provide a structured representation of objects, their relationships, and spatial information within the environment. This allows the LLM to reason about the environment in a more organized and efficient manner. It's crucial for understanding the context of user commands and for planning actions that are both semantically and spatially correct. The system uses this information to extract relevant details for planning and to update its understanding of the environment as the robot interacts with it.
The architecture includes a controller and an explainer module. What are their respective roles in ensuring robust and adaptive task execution?
The controller monitors the execution of actions and detects errors. If a failure occurs, it sends a failure message to the explainer. The explainer analyzes the failure, searches a database of past experiences for similar failures and their solutions, and provides suggestions to the task planner on how to adjust the plan. This feedback loop allows the system to learn from its mistakes and adapt its strategies in real time.
The paper describes the implementation on the Robi humanoid robot. How does the system's architecture account for the robot's specific capabilities and limitations?
The system's design explicitly considers Robi's physical capabilities, such as its degrees of freedom, sensor suite, and manipulation abilities. The skill planner translates high-level skills into low-level commands that are executable by Robi's hardware. The controller and executor modules are also tailored to Robi's specific hardware and software interfaces. This ensures that the planned actions are feasible and safe for the robot to execute.
The preliminary results show varying success rates across different request types. What insights can be drawn from these results, and what are the future research directions?
The results indicate that the system performs well on simple and moderately complex requests, but struggles with more open-ended, complex requests. This highlights the challenges of natural language understanding and reasoning in highly ambiguous situations. Future work will focus on improving the LLM's ability to handle ambiguity, expanding the explainer's dataset through autonomous learning, and enhancing the system's proactive information gathering capabilities. We also need to address the limitations of LLMs in pragmatic understanding and improve the system's reliability at both the planning and communication levels.
The paper mentions the potential for autonomously expanding the explainer's dataset. Could you elaborate on the methods and challenges involved in such an approach?
Autonomously expanding the explainer's dataset involves automatically logging successful and failed task executions, along with contextual information such as the user request, environmental state, and robot actions. This data can then be used to train or fine-tune the LLM's ability to generate effective suggestions for handling failures. Challenges include ensuring data quality, handling noisy or incomplete data, and developing efficient methods for storing and retrieving relevant information from the growing dataset. We also need to consider privacy implications if the dataset includes sensitive information.
The discussion of proactive information gathering is intriguing. How might the system be designed to proactively acquire information relevant to task completion rather than solely reacting to failures?
Proactive information gathering involves equipping the system with the ability to anticipate potential challenges and acquire relevant information before they become obstacles. This could involve using the LLM to generate hypotheses about potential problems, querying the environment through sensors or other means to verify these hypotheses, and adapting the plan accordingly. This requires integrating advanced planning techniques, such as hierarchical planning or Monte Carlo tree search, with the LLM's reasoning capabilities. The challenge lies in balancing the cost of information acquisition with the potential benefits of avoiding failures.
The paper mentions the limitations of LLMs in pragmatic understanding. How might these limitations affect the system's performance, and what strategies could be employed to mitigate them?
LLMs can sometimes generate outputs that are logically consistent but pragmatically inappropriate for the given context. For example, an LLM might generate a plan that is technically correct but physically impossible for the robot to execute due to its limitations. Strategies to mitigate this include incorporating explicit knowledge about the robot's capabilities and limitations into the LLM's context, using reinforcement learning to train the LLM to generate more pragmatically sound plans, and incorporating human-in-the-loop mechanisms to validate and correct the LLM's outputs.
The integration of human-in-the-loop mechanisms is a crucial aspect of building trust and reliability in robotic systems. How could human feedback be effectively incorporated into the system's learning and adaptation process?
Human-in-the-loop mechanisms can be implemented in several ways. For example, humans could provide feedback on the LLM's suggested plans, correct errors in the LLM's reasoning, or provide additional information about the environment or task. This feedback can be used to fine-tune the LLM's parameters, update the explainer's dataset, or improve the system's overall performance. Careful design is needed to ensure that human feedback is efficient and effective without placing an undue burden on the human user.
The paper focuses on task execution in relatively controlled environments. What are the key challenges in extending this architecture to more complex and unstructured real-world scenarios?
Extending this architecture to more complex real-world scenarios presents several challenges. These include handling greater uncertainty and variability in the environment, dealing with noisy and incomplete sensor data, managing interactions with multiple agents, and ensuring the system's safety and robustness in unpredictable situations. Addressing these challenges will require advancements in several areas, including robust perception, advanced planning techniques, and more sophisticated methods for handling uncertainty and ambiguity.
The use of cosine similarity for comparing user requests in the explainer module is interesting. What are the advantages and limitations of this approach, and are there alternative methods that could be considered?
Cosine similarity offers a simple and efficient way to measure the similarity between user requests represented as vectors. Its advantage is its computational efficiency and ease of implementation. However, it has limitations in capturing more complex semantic relationships between requests. Alternative methods include using more sophisticated embedding models, such as sentence transformers, or incorporating techniques from natural language processing, such as semantic role labeling or dependency parsing, to capture richer semantic information. The choice of method depends on the specific requirements of the application and the trade-off between accuracy and computational cost.
The paper concludes by mentioning the need to assess the system's reliability at both the planning and communication levels. What metrics could be used to evaluate these aspects, and how could the system be designed to improve its reliability?
Evaluating the system's reliability requires a multifaceted approach. At the planning level, metrics could include the success rate of task completion, the number of replanning events, the time taken to complete tasks, and the robustness of the system to unexpected events. At the communication level, metrics could include the accuracy of natural language understanding, the clarity and effectiveness of the robot's responses, and the overall user satisfaction. Improving reliability involves enhancing the LLM's reasoning capabilities, improving the robustness of the perception system, developing more sophisticated planning algorithms, and incorporating mechanisms for error detection and recovery. Continuous monitoring and evaluation are crucial for identifying areas for improvement and ensuring the system's long-term reliability.
The integration of LLMs in robotics is a rapidly evolving field. What are some of the most promising future research directions in this area?
Several promising research directions exist. One is the development of more robust and efficient LLMs specifically tailored for robotic applications. Another is the integration of LLMs with other AI techniques, such as reinforcement learning and imitation learning, to improve the system's ability to learn and adapt. Further research is needed on developing more sophisticated methods for handling uncertainty and ambiguity in real-world environments. Finally, significant work is needed on addressing ethical and safety concerns related to the deployment of LLMs in robotic systems.
The paper emphasizes the importance of seamless collaboration between humans and robots. How can the design of human-robot interfaces be improved to facilitate more natural and intuitive interaction?
Improving human-robot interfaces requires a multidisciplinary approach, combining insights from human-computer interaction, cognitive psychology, and robotics. This includes developing more intuitive and user-friendly natural language interfaces, providing clear and informative visual feedback, and designing interfaces that are adaptable to different user skill levels. Furthermore, research is needed on developing methods for effective communication and collaboration between humans and robots in complex and dynamic environments.
The use of hierarchical task networks, HTNs, for skill decomposition is mentioned. What are the advantages and limitations of using HTNs in this context, and are there alternative approaches that could be considered?
HTNs offer a structured way to decompose complex tasks into smaller, more manageable subtasks. This hierarchical structure facilitates planning and allows for efficient replanning in case of failures. However, HTNs can become complex to manage for very large and intricate tasks. Alternative approaches include using probabilistic planning methods, such as Markov decision processes, MDPs, or employing more flexible planning paradigms, such as anytime planning or reactive planning. The choice of method depends on the specific characteristics of the task and the desired level of planning sophistication.
The paper mentions the use of, in context, learning to influence the behavior of the LLM. Can you elaborate on how this technique is applied in this architecture and what are its advantages and limitations?
In context, learning involves providing the LLM with examples of desired behavior within the input prompt. In this architecture, the LLM's context is updated with information about the current task, the robot's state, and the results of previous actions. This allows the LLM to learn from its past experiences and adapt its behavior accordingly. The advantage is that it allows for efficient adaptation without requiring explicit retraining of the LLM. However, in context, learning can be sensitive to the choice of examples and may not generalize well to unseen situations.
The paper focuses on the planner module, with details on the perception module deferred to a separate article. What are some of the key challenges in designing a robust and efficient perception system for this type of robotic application?
Designing a robust perception system for this application requires addressing several challenges. These include handling noisy and incomplete sensor data, fusing information from multiple sensors, accurately identifying and tracking objects in dynamic environments, and efficiently representing and reasoning about the environment. Advanced techniques such as sensor fusion, object detection, and scene understanding are crucial. The system must also be computationally efficient to allow for real-time processing of sensor data and rapid adaptation to changes in the environment.
The success rate for complex requests was significantly lower than for simpler requests. What are the key factors contributing to this performance difference, and how could the system be improved to handle more complex and ambiguous instructions? The lower success rate for complex requests is likely due to several factors. These include the increased ambiguity and complexity of the instructions, the need for more sophisticated reasoning and planning, and the potential for unforeseen challenges during task execution. Improving the system's ability to handle complex requests requires advancements in several areas, including natural language understanding, common sense reasoning, and robust planning and execution capabilities. This may involve incorporating more advanced AI techniques, such as knowledge graphs, symbolic reasoning, and reinforcement learning. This has been a comprehensive discussion on the key aspects of this research paper. Thank you.